are the topics we're going to discuss in this video. So first, we're going to talk about how to sketch a slope field for a given differential equation. And when they give you the differential equation, it's going to be solved for y prime, or it's going to be solved for dy dx. It has to be, because we're going to sketch a slope field. The slope field consists of slopes, and that's what the first derivative is. It gives you the slope at any given x value. Next, we're going to be given a slope field, and we're going to be asked to sketch a particular solution through a given point. So this is when you're going to have the field given to you, and it's going to have all these slopes everywhere on the xy plane, and they're going to tell you which point they want you to go through, and then you have to just connect the slopes, kind of go with the flow, like you're in a river going with the stream. So that's going to be that portion of this video. Next, we're going to ask you to match the slope field already created to the differential equation that created it. So you're going to have a slope field over here with all these slopes here. And then your choices, A, B, C, and D in a multiple choice, are going to be y prime equals something, or dy dx equals something. So you're matching the slopes of the given field to this differential equation that's solved for the derivative. Finally, you're going to be asked to match a solution. When you see the word solution to a differential equation, that's when they're looking for the equations of anything that you might create by going with the flow. So for example, if they give you a field and you connect the slopes and you get a quadratic looking function, then one of your answers is going to be yx squared plus c, because you're going to see a family of these quadratic functions when you connect the slopes. But the important thing is, if you see the word solution, you're going to see your answers as y equals something, not y prime, not dy dx. Okay, again, the topics we're going to cover: sketch a slope field for a given differential equation. They're going to give you this blank grid, and they're going to give you a differential equation solved for y prime. All right, you might see it as y prime equals x plus y. And in this video, we're going to talk about how to go from this differential equation solved for y prime or dy dx and how to create a slope field. Here, they're going to give you a slope field and they want you to sketch a solution curve. Whenever you see the word solution curve, you're going to be drawing through the ebb and flow of this slope field. Now, they're going to try to trick you here. Sometimes they'll tell you exactly where you want to go through, the point 2 comma -1. So that would be through this point right here. And then you would connect the slopes emanating from that point as best you can, just kind of going where the slopes take you. All right. Now, other times, they're going to try to disguise the point by having this vernacular: f of 0 equals 2, y of 3 equals 2. If they do that, just remember, this is the x coordinate. That's within the parentheses, and that's your y coordinate. That's your input, that's your output. So if you see f of 0 equals 2, they want you to go through the point 0 comma 2. If you see y of 3 equals 1, that is still asking you to look through the point x equals 3 and y equals 1. Remember, that is the input. Again, continuing with the topics covered, match the slope field created to the differential equation that created it. So again, you see this is the differential equation solved for y prime. So here you're going to match the slopes created by any xy coordinate in this field that you plug in. You are not looking for solutions here. This has nothing to do with creating graphs by connecting the slopes and trying to determine like this. Okay, you might be tempted to do that, and if they had a choice here, dy dx equals x squared, you'd be tempted to match these two, but that's not what they're looking for here. Here, you don't see the word solution. So if you don't see the word solution, you're not connecting. If you don't see y equals, you're not connecting. Here, if you just see dy dx, that means they're just looking for the equation, the slopes that created the field. Okay, here now, we're going to see the word solution. So if you see the word solution, that's your indication that you have to connect the slopes. So here you see the solution and the word solution, and also you see these are solved for y. So if you see the word solution, if you see the choices are solved for y, here is where you have to go after them. So for example, here we're going to connect these slopes here. If we connect these slopes, you could see that creates the line or the solution y equals 1. So therefore, that's going to be your choice that matches that graph. We have a differential equation shown here, a relatively simple one, and you'll see it written as either dy dx equals this right side of the equation or y prime. So let's first ask ourselves, what is a differential equation? And then we'll talk about what does a solution to a differential equation even mean. Okay, here is a nice simple definition of a differential equation. It is an equation that contains an unknown function along with one or more of its derivatives. So if we focus here on this side using y prime, we could see that that differential equation contains this unknown function y along with its derivative. Now, as we'll see, differential equations can get a little bit more complex. But again, these examples of differential equations meet this definition. You have an unknown function, that's your y, that is a function, together with one or more of its derivatives. Here you see its first derivative, and here you see its second derivative along with that unknown function. Now in a moment we're going to talk about solutions to differential equations, but in essence this is what it is. The solution to the differential equation is if you find the unknown function. So let's say this is the solution to, let's work on the lowest, more complex example. Let's say we find that this function is the solution, or we think it is. Next thing we're going to do is we're going to take its first derivative, whatever that is, and then we're going to take its second derivative, whatever that is. And then, folks, we're going to go ahead and systematically plug in these entities into the original differential equation. So we're going to plug what we think is the solution, what we think is the unknown function for y. Then we're going to plug in the first derivative of what we believe that function to be for y prime. And then finally, we're going to take what we believe to be the second derivative of the unknown function and plug it in or substitute it in for y double prime. And when we do that and we simplify, the idea is to make sure that the left side of this differential equation equals the right side. the right side. And if that is true, if we get this scenario where the left side equals the right side, then we have what we call in math an identity, meaning this is going to be true for all values of x. X is the independent variable, that's the input. If we feel we have the solution of this differential equation, again, what does the solution mean? It's the unknown function y. If we feel we have it, we take its two derivatives and we plug it in and we get left equal right, we have established an identity, and that confirms that that is indeed the solution of this differential equation. In this first example, we are given the differential equation on the left, and we are asked to show that this indeed is the solution to this differential equation. Again, a differential equation contains an unknown function and its derivatives. Here, the one that we're proposing or analyzing doesn't even have the original function. All we have is its derivative. Okay, so what we're going to do is we're going to take the derivative of the proposed solution. And when we do that, we find that y prime equals 2x. Now, we don't have to take the second derivative because the second derivative does not exist in the differential equation. Next is to take this derivative and plug it into the differential equation. So you could see we're going to take y prime equals 2x, and we're going to substitute instead of y prime, we're going to have 2x, and of course that equals the right side of the equation. So if you have the left side equaling the right side, we have an identity, which means this is going to be a solution. Y equals x squared is a solution to this differential equation for all values of x. A moment ago, we proved that y equals x squared is a solution to this differential equation. But folks, it's important to know that there could be many solutions to the differential equation, and also there could be none. For example, this also would be a solution to this differential equation, all right? Or this would be a solution to this differential equation, and therefore you can create the general form of a solution to this differential equation by using a plus c. And that's because when you take the derivative of each of these, or any constant that you plug in there, you're going to be left with 2x. Now, folks, this is not always the case. You can't always just willy-nilly add a constant to your solution. And in the next example, you're going to see an example where you're not allowed to just add a constant like that. You have to be judicious. In our next example, we are given this differential equation. As you can see, this matches the definition of a differential equation. It contains an unknown function. Here we have the function y along with one or more of its derivatives. Now, folks, I want to draw your attention to the difference between this differential equation and the one we worked on previously. The previous equation was solved for y prime, so we were able to say that this was dy dx. But here we can't do anything like that. We can't say that dy dx equals that. That makes no sense. We have two equal signs. So if you see that you are not solved for y prime, you cannot add the dy dx equaling to this equation. Okay, with that said, let's proceed to prove that the solution on the right is indeed the solution to this differential equation. The idea is when we take this unknown, this is an unknown function, we're suggesting that this is the function that satisfies the differential equation. Okay, first thing we need to do is take y prime. When we take y prime, we rewrite what we see, which is e to the negative 3x, and with the chain rule we have to take the derivative of the exponent and we get a negative 3 out front. The next term goes from 2x to just 2, and the plus 3, the derivative of that is 0. So now we do not need to take the second derivative here, so let's go ahead and substitute what we have. Here is our first derivative of our proposed solution. We're going to add that to 3 times our proposed solution and see if we do indeed achieve the right side of the original differential equation, thus establishing an identity. So if we go ahead and we distribute this 3, we're going to get plus 3e to the minus 3x plus 6x plus 9, and then rewriting here, we're going to have 3e to the negative 3x plus 2. These are going to cancel, the plus 3 and the minus 3e to the negative 3x. We're going to have 6x equals 9 plus 2, 6x plus 11 on the left side of the equation, and indeed that does match the original right side of the equation. So if we have the right side equaling the left side, then we have an identity, thus establishing that that is indeed a solution. Okay, folks, I want to leave some of this math up here to show what I was mentioning before. You can't willy-nilly just substitute a different constant here. So if we were to say that instead of this being our solution, we just change that constant from plus 3, say, to plus 9, look what happens. When we distribute that 3, we get 3 times 9 is 27. And indeed, if you have a 27 here, 27 plus 2 is going to give us 6x plus 29 equals 6x plus 11. And clearly, that is not true. Therefore, changing that constant randomly to a different constant is not valid. Let's now move to the topic of a slope field, what it is and why we even create them. A slope field is a graphical representation of a differential equation. The slope field depicts the slope of the differential equation at every point on the xy plane. I say every in quotes because of course we're not going to look at every point, but we certainly are going to look at a lot of them. This is a differential equation. You could see there's some unknown function here that would solve this differential equation. Notice, we are going to go from this differential equation, which is solved for y prime, because that's its derivative, and its derivative is the slope of the differential equation. And here in these miniature line segments, there are slopes depicted at every point on the xy plane, at least in the range that we're looking at. Okay, so the way you create a slope field from the differential equation, and again, it's going to be solved for y prime, or it's going to be solved for dyx before you can create the slope field, is we're going to build a table. And on that table, you're going to have the following. You're going to have the point itself, which is going to have an x and a y coordinate, and then the derivative there, otherwise known as the slope at that point. And here you could see the derivative depends on both the x and the y. That's not always true, but in this particular case it does. So let's look at where the slope would be 0. So that would be where y equals x. So let's look, we're at 1, 1, and you can see if you go to 1, 1, we have a little horizontal line segment which depicts a slope of 0. And if you look throughout the slope field, you could see everywhere x equals y, you're going to have a slope of 0. Okay, now let's look at this particular point, 2, 0. So at 2, 0, you're going to have an x value of 2, a y value of 0. If you plug that in, you're going to have a slope of 2 minus 0, or 2. So if we go to that point, 2 comma 0, you could see you have a positive slope that's a little bit steeper than, say, a slope of just positive 1. All right, positive 1 we would get where x equals 3 and y equals 2. Let's see where that is. 1, 2, 3, 1, 2. So right there, that would be a positive slope of 1. Okay, now, once you have your slope field, this is a collection of general solutions. And the way this will be presented to you is you might be asked to find a particular solution, and they'll give you an initial condition of a point, and they'll ask you to find the particular solution that goes through that particular point. And in the next segment, I'm going to show you how to glean the particular solution from this array of general solutions. And basically, it involves following the flow of the slopes. So getting to the point they give you and following the flow, almost like this is current in a river, and that will eventually give you a curve that represents the particular solution of that differential equation that includes a particular or specific point. Let's now go back to this differential equation for which we have a slope field and see if we could find a particular solution that includes the point -2 comma 3. You'll also see it in a problem on your homework or quiz written as satisfies the initial condition y of -2 equals 3 or f of -2 equals 3. This is very confusing. If you see y of -2 equals 3, they're still saying that the x coordinate is -2 and the output, the y value, is 3. So let's go to that point in our slope field, -2 comma 1, 2, 3, right here, and let's see if we can extract or draw a particular solution that goes through that point or has that initial condition. So folks, what you do here is you kind of go above and below the point, and so let's start above here. I'm working in light blue, and I'm coming through the point, and then I'm following the slopes. You just kind of go with the flow here. And then you see here, this is a local minimum. That slope is 0. And then we have to honor what looks like some sort of oblique asymptote here. So this would be a particular solution that goes through that point. Now, if they didn't give us a initial condition or a particular point, let's see if we could find a particular solution from this graph. Well, look what we have going on here. We have that oblique asymptote. So if we were to draw a line right there, just connect all those points, that line, would have a slope of 1, because look, it goes from corner to corner in each of the parts of the grid, which means your run is 1, your rise is 1. Run is 1, rise is 1. And also it goes through the point, the y-intercept of -1. So folks, this solution is y equals x minus 1. Now let's prove that using the techniques that we did earlier in this video. So if we think this is a solution to our differential equation, let's take its derivative, and y prime is going to equal 1, and then let's substitute these entities into the differential equation and see if we get the right side equal the left side. Okay, so y prime is going to equal 1. We're going to have x minus what we believe to be the function, the solution, which would be x minus 1 replacing y. So we're going to get y equals x minus x. I'm sorry, 1 equals x minus x plus 1. And indeed, we do have an identity. So we showed that this is one of the solutions to this differential equation, and we were able to extract it from the slope field. So this goes back a few slides ago when I said, why do we do the slope fields? Well, here's why. Sometimes we're faced with a differential equation that we're unable to solve with standard techniques. And we're going to go over those techniques in a future video, but for example, separation of variables, where you bring all the y's and the dy's to one side and all the x's and dx's to the other side, and then you integrate both sides and see if you can solve the differential equation. But sometimes they're not solvable or not easily solvable. And in those scenarios, one technique is to build a slope field and see if you can get an approximation of the solution to the differential equation. Because sometimes in everyday life, an approximation of the solution is good enough. So that's the reason for learning about slope fields. Differential equations that are not solvable by standard techniques. Before I forget, I want to show you how to find a beautiful slope field calculator on Desmos. And what you do is you Google these three words, slope field generator, and you'll be brought to this Desmos calculator. And here's what you have to enter. You have to enter this first part. This is what I typed. Let g of x comma y equal dy dx. And then you have to type this in, g of x comma y, and here is the particular differential function that you wish to have the slope generator. So again, when you generate a slope field, you must have this as dy dx equals negative y over x. And this is what you type in to get your field created by Desmos. Folks, I couldn't find this just going to desmos.com. I'm not smart enough. Maybe it's easy to do it. But again, if you Google those three words, slope field generator, it'll bring you to this window. Next, we have this differential equation, dy dx equals x, or we can write it as y prime equals x. And we have generated this slope field. Here I entered in the differential equation right here. Again, it has to be solved for y prime or dy dx to generate that slope field. And what we're going to try to do here is extract one of the solutions. This is an array of general solutions. So if we take a look here, we could see that this is going to be a local minimum here in light blue. And if we follow that in both directions, it looks like we have something like this. We're just following the slope as best we can. It might be hard to see because of all the colors, but basically I think this looks like a general form of what our solution to the differential equation might be. Well, again, if you're dealing with an unsolvable differential equation or very difficult to solve, at least you could see that the family of functions is going to be quadratic. So I'm going to take a shot at this and say this is a wide parabola that's facing upwards. So I believe that the coefficient is going to be less than 1. So let's see if this is a solution to the differential equation. And I have a plus c here because clearly you can go up and down the y-axis and you can put in any constant here. So let's go and see if this works. So we're going to take y prime. So y prime is going to end up being just x. And lo and behold, if we take this derivative of what we believe to be a solution, and we go to the original differential equation and we plug in x for y prime, we do get an identity. So that indeed is the solution within the slope field graph. Let's just prove this algebraically. If we were to solve this using the separation of variables technique, here again, here's our differential equation, dy dx equals x. We're going to put the x's and the dx's on that side and the y's and dy's on that side. What we did is just multiply both sides by dx. We're going to take the integral of both sides, and the integral of dy is y, integral of x dx is x squared over 2, and then we only have to add 1 plus c. In other words, we could have had a y plus c over here, but we just use the 1 plus c on one side of the equation to account for both of those plus c's. So you can see we confirmed that y equals 1/2 x squared plus c is a general solution for the slope field that we just examined that pertain to this differential equation. Next, we are asked to match each slope field with its respective differential equation. The first thing we notice is that these choices are solved for y prime. They're solved for dy dx. Therefore, we're just going to be looking at the slopes here. We are not, for example, going to be drawing in any solution. You don't see the word solution, find solution here. You don't see the choices solved for y. They're solved for y prime. That is the slope. Okay, so let's look at y equals sine of x, and I try to look where there's a zero slope, because that's often going to give you the most information. So right here we see a zero slope at, it looks like y equals 2, and the problem is that this doesn't change as x changes. This differential equation only depends on the x. So what we're looking for is something that stays constant when you're at a given x value and the y values are changing. So that brings me to this graph C. So here we have when x equals 0, the slope is 0. When x equals 0, the slope is going to be 0 because sine of 0 is 0. So this is going to be y equals sine of x. Remember, we're looking for the slope. Next, for number 6, we're looking for where the slope equals the x minus the y coordinate. So first thing I look for is where are the slopes 0, and we are going to find the slopes equal to 0 when the x value equals the y value. So that's going to bring our attention right here. If x equals 1 and y equals 1, we are going to get a slope of 0, so this is going to match with choice D. Okay, for the next one, we're looking for something that depends on the y value only. So the y value, the slope is going to stay the same over a particular y value. So we see that happening here. So let's investigate this one. So if we put in y equals 2, we will get 0. Therefore, this is going to be choice A. All right. Now we know the answer is going to be B, but let's just confirm it. Here, the x and the y, when they are opposite to each other, we're going to get a 0. So we're looking for something like this. X equals -1 and y equals +1, giving us a 0. And indeed, we have that here. -1, +1. So this would be choice B. This next problem, number 5, combines some of the elements we've been talking about. First, it has this differential equation solved for its slope, and it's telling us that that generated that slope field. Now they bring up the word solution, y equals g of x, and they want the solution to match the initial condition, -2, -1. So remember, like we talked about earlier, that is going to be your x value, that is your y value. So let's go to -2, -1, and that's going to put us about right here. Okay, so we want to draw the solution because look, it's solved for y. You see the word for solution. That is when we start to draw and go with the flow within the slope field. Okay, now look what's happening here. It's hard to see, but it looks like the slope here is 0. And if we're not 100% sure, we can go back to the slope formula that they give us. And if we plug in y equals 0 here, we see that these slopes are going to be 0. So it appears that we have some sort of asymptote here, a horizontal asymptote where the slope is going to go to 0. And they want to know the limit of g of x, the limit of this solution as x goes to infinity. So let's go ahead and draw through this here in yellow. And we're kind of going with the flow here, but then we hit this asymptote and it looks like it's going to approach 0. So this would be choice C. In problem 16, we are asked to sketch the slope field. Again, this differential equation is solved for its slope. So the best way to do this is to make a table and then look for patterns that might speed up the process. All right, so we see when x equals 1 and y equals 1, the slope is going to be 1/2. When x equals -1 and y equals 1, the slope is going to be -1/2. When x is 0, the slope is going to be 0. When y is 0, the slope is going to be 0. And let's go ahead and plot these and see where that takes us. Okay, so when x is 0, we're going to have a 0 slope, and that's going to be true no matter what the y value is. And when y is 0, the slope is going to be 0, and that's going to be true no matter what the x value is. Next, we have x equals 1, y equals 1. We have a slope that's +1/2. And -1, +1 yields a slope of -1/2. So it appears that we have some symmetry over the y-axis. So let's do one more point here. 3, 1 is going to give us a slope of, let's see, 2, 1 is going to give a slope of 1. So that's going to be a little steeper, like so. And then therefore that's going to be symmetric in the negative direction. Then we'll do a few down here really quickly. If x is -1 and if x is +1, y is -1, this is going to be -1/2. So something like this, a little flat, and then therefore that's going to be the mirror image there. And when x is 1 and y is -2, this slope is going to be -1, and therefore this one's going to be flipped. So if you continue on, you will go ahead and get your slope field. In part B, we are told that f is a function that satisfies the differential equation. So again, solutions, we're talking about going through and drawing an actual solution through the slope field. Plus you see it has the curve set y equals. That means you're drawing. All right, so they want an equation for a line tangent to the curve. So we don't need the equation of the solution curve itself. All we need is the line that's tangent to it at that point. Well, to get a line tangent to any point on any curve, all we need is the slope and a point, and we can use the point slope form. So they wanted to go through 1, 1. Of course, I picked the wrong point. It would be right here. So it's going to go through that point. So what we need is the slope at that point. So the slope is given by this formula. So 1 times 1 is 1 over 2 is 1/2. And we have the point, which is 1 comma 1. So we're going to go ahead and use the point slope form. The way I like to do this, here's the slope form, that point slope form that is taught in class. What I like to do is change this little 1 to a p, because that makes it clear that that's where the point goes. And then I just move it to the other side. So what I like to use is y equals positive yp plus m times x minus xp. We have our slope, and we have our yp is 1 plus 1/2 x minus 1. So that would be the line they're looking for. And then they want to use that to estimate the value of f of 1.2. And what we would do is just use this line and do 1.2 minus 1. And when we do all the math, we would get 1.1. And the theory, folks, is that, let's say this graph looks like this, all right, that we're talking about. Let's say we draw a line through all the ebbs and flows of the slopes in the slope field, and we get this curve right here. What they're saying is that this tangent line right there, that's at x equals 1. They're saying that that tangent line right there is close enough so that if we go to x equals 1.2 right there, they're saying if you get the y value on that tangent line, that y value is close enough to the y value you would get if you were actually on the curve. So this tangent line provides an approximation, a linear approximation. This would be f of 1.2 if you're actually on the blue curve, but this is the value here if you use the tangent line. Here's the value if you actually use the curve, and what we're saying is that those 2 points are close enough.